Hi, I'm Randall Heyman, a mathematics academic. Welcome to my Corona Help playlists, where I make quick turnaround videos to help educators and students during the coronavirus outbreak. If you'd like me to make a video for you, then just write me a comment below any of my videos, or if you like, you can drop me an email. Okay, so Benny has contacted me from California and wants me to solve this problem, or show him how to solve this. He actually sent me an email which has got sort of questions trying to fill in bits of it. It's a bit confusing to me. So I thought what I'd do as a start is I'll just use the first isomorphism theorem to come to terms with this specific isomorphism that we can see here. Okay, so the way I want to do this is I'll just normally Wikipedia is I think it's confusing if you don't know what you're looking for in mathematics, but here I'll actually just write out straight from Wikipedia, and then we'll see how we can adapt it. So this is the first isomorphism theorem for rings. There's also isomorphism theorems for groups and other things as well, but this is the one for rings. It's the same sort of concept. Let R and S be rings. And let phi, so phi is a function that takes the elements of R and maps it onto some or all of the elements of S, and it's going to be a ring homomorphism. Okay, so I'll just scratch out here. I don't so for it to be a ring homomorphism, what we require is, I've done a video on this in the last couple of days, so last week I think. So have a look if you want to see more about this. I think I might have done group homomorphisms, but the ring, no, it was rings actually. So okay, we're going from R to S. So if we have the phi A B, actually let's do it in the order you normally would see it. The first is you need the group homomorphism aspect. So if you add phi of A plus B, you'll get phi A plus phi B, which is just saying it doesn't matter whether you add first and then apply the phi, or apply the phi and then add. Phi A times B equals phi A times phi B. And finally, you need that phi 1 is equal to 1. So I've done that in a previous video. I'll probably will refer to it here, but I'm not going to go through a proof that something's a ring homomorphism. I don't think it's pretty easy. If you've got questions on it, just let me know if you want to go down that path. Okay, so I'm sort of explaining this as we go a bit. Okay, so what happens if we satisfy these conditions? Then the first thing is 1, the kernel of phi. Remember, that's just all the things that send phi to 0. Sorry, that's all the elements of R that phi sends to 0. So that's saying that that's an ideal. The kernel itself is an ideal of R. Okay, that's interesting, but we don't need that. 2, the image of phi is a subring of S, S. So I'm saying the image is obviously it's a subset of S, because phi maps R to S, which we add up here. So it's clearly a subset. What this is saying, it's actually a ring itself. So the image of phi will be a ring itself sitting within S. And then the final one, which is the important one for us, I think here, is the image of phi is isomorphic to the quotient ring. Now, I haven't done a video on quotient rings, but I've done one on quotient groups, and the concept is pretty much the same. So here we see this nice relationship between the quotient ring and the kernel. Okay, so the easiest way, well, the first thing is let's just make a few comments and then I'll draw the all-important triangle that makes everything clear. But for what we're doing, if we just cast our eyes back up here, you have to be able to fit what you can see here from Wikipedia to your problem. So in this case, we've got R and S. Well, sorry, in our case, we've got ZX. ZX is going to be R. Z is going to be S. The kernel of phi is going to be this that we've got here, this the ring generated by X. What is the ring generated by X? We've talked about generated groups and rings in the previous videos, but it's basically just saying everything that you can construct just using X. So you can repeatedly add it. X plus X plus X is 3X. Multiply it by X squared and you get 3X cubed. So 3X cubed is generated by X. And in fact, all the polynomials are generated by X except the ones that have a constant that is not equal to 0. So you can't use this. If you generate X, if you generate using X, you can't get X squared plus 1, for example. And that'll become important as we go on. Okay, so I think we're ready to draw the triangle, which you'll see in a lot of books for how this all works. So what we have here is ZX, the ring of polynomials with integer coefficients. And we're now talking about having a phi which will map onto Z. And the way to think about phi is we can actually specifically create a function that does this. If we think about it, we need a function. It has to be a ring homomorphism, and it has to map all the polynomials to the integers. And the natural one to think of is that you take the polynomial p of x, and when you apply phi, you get just the constant coefficient, which is just p of 0. P of 0 just generates, by putting 0, you just get the constant coefficient. So, example, I'll just do it small because I know I'm going to need more space here. Phi of x squared plus 8 equals, well, if you just put a 0 in for x squared, you'll just get 8. So that's not too hard, I don't think, to come to terms with. Okay, now let's just think about what's the kernel of phi, because we're going to need that. The kernel of phi is all the polynomials, in this case obviously with integer coefficients, that map to 0, or that are mapped to 0, that map to 0. So you think about it, this one here, this is not part of the kernel, because when I map it I get 8. So if you think about it, the kernel, think about it a bit, the kernel of phi is equal to, essentially what I'm saying is it's all the polynomials p1x, notice there's no coefficient there, no constant coefficient, p2x plus ... and I'll put here plus pm x to the m, where m is an integer greater than or equal to 1. So it's all the and obviously all the coefficients are integers in everything we're talking about here. So it's all the kernel. This kernel is just all the polynomials with no constant, or if you like, a constant of 0. Okay, so then what is it saying? The image of phi. So the image of phi is this. So this is what the isomorphism theorem says. that it's isomorphic to, so I'm going to draw down here, ZX. So it's saying that this thing here, Z, is isomorphic to Z quotiented out by the kernel of phi, which is, we talked about that there, so that's just X. So what this is saying is that there's this isomorphism here. Let's call the isomorphism mu. So, which is exactly what we are required to show. So I suppose if you're going to, whoops, if you're going to go back here, so I suppose the important things here are, so RS are rings, which they need to be for this. Phi is a ring, well, yeah, as I've sketched it, drawn it, phi is a ring homomorphism. I'll leave you to check that and just ask me questions via comment or email if you can't show that it's a ring homomorphism. And so then the conclusion is, so what it says is that this quotient ring is isomorphic to Z. Now, just to give you a little bit more intuition about this, what have we got here? We've got polynomials. So we've got, you know, I could write a whole lot of polynomials here, x squared plus 1, 0, 5, x cubed, ... So here's my polynomials. Now, I've got we don't specifically need to spell it out for the question, but there's another function here, let's call it f, which maps these polynomials to the quotient ring. And what does this here consist of? Well, I can actually write this out very implicitly. This is equal to the set, or the ring. And what it is -1, 0, 1, ... And here I've used these square brackets to indicate an asset class. And in it, I've put a representative of that asset class. So what is -1, for example? That is the set of all polynomials with a coefficient of -1. So it's -1 plus p1x plus ... plus pm x to the m. M is greater than equal to 1. And as we've said, all the coefficients are integers. So that's what this looks like. And up here, we've got Z here. And Z is just equal to ... -1, 0, 1, 2, ... They're the integers. And I hope you can see that there's a very natural isomorphism between this and this. They're basically the same. They certainly satisfy all the conditions for it to be a ring isomorphism, which you can show, and if you have problems, let me know. But it's pretty clear to see here that mu is we can construct this isomorphism mu, which maps Z to ZX quotient to that. And what's the function? Well, mu of some integer Z, say j, equals just the equivalence class containing j. I mean, that's all this is saying. It's not, this is, I remember when learning this the first time, it seems incredibly convoluted and difficult. And there are difficult bits of it, but the end result here is actually very, very simple. It's just saying that this is very similar to this. That's really what it's saying. Okay, Look, there's a lot there. I hope I've tried not to be too formal and dry about this and try to give you a really good sense of what's going on here. Remember, with this theorem, the triangle is your friend. Any problem, your first thing should, well, one of the things you should definitely do is draw the triangle and try and use that to help you work it out. Okay, that's all I wanted to say here. I hope that's helped Benny and anyone else who's interested. If you've got questions on this or anything in mathematics, just comment or email me. And if I think I can help you, I will try to do so.